Welcome to the Kalopa Mission Control Podcast. I am your host, and it is a genuine pleasure to have you join us for episode number 4. If you have ever stood on a quiet shoreline at dawn, watching the grey, bruised swells of the ocean roll in to meet the land, you will know that the sea has a way of commanding our absolute respect. It is an ancient, rhythmic world, operating on a scale and a timeline that humbles our brief human existence. Here at Kalopa Robotics, our work is entirely bound to the whims of that great, restless expanse. We build small, autonomous sailing vessels designed to survive the deep ocean, listening to its secrets and returning that data safely home. But before we look at the engineering of our own small fleet, I would like to take a step back. I want us to look at the macro picture, the state of the global ocean, and the shifting tides of how we, as a global community, are choosing to protect it. How do we protect what we cannot see? This is where the intersection of marine biology and advanced technology becomes so thrilling. Just recently, a collaborative project known as Deep Vision, led by the Plymouth Marine Laboratory and the University of Plymouth, has begun using artificial intelligence to map vulnerable marine ecosystems across the Atlantic. For decades, robotic submarines have captured thousands of hours of deep-sea footage, but reviewing it manually takes human analysts months, if not years. By harnessing artificial intelligence, researchers can rapidly identify fragile deep-sea habitats, such as ancient coral reefs, sponge gardens, and fields of sea lilies. These organisms are the deep ocean equivalent of old-growth forests, providing shelter and sustenance in the lightless depths. Mapping them accurately gives our policymakers the evidence they need to draw the boundaries of new marine protected areas where they will do the most good. But protection, we are learning, is often fragile and subject to the pendulum of political will. Consider the Northeast Canyons and Seamounts Marine National Monument, located off the coast of New England. It is a spectacular seascape. Beneath the waves lie canyons that rival the Grand Canyon in scale and submerged mountains as tall as the Appalachians. It is a critical winter foraging ground for seabirds, including the beloved Atlantic puffin, and it harbours deep water corals that have been growing quietly in the dark since the days of the Roman Empire. Recently, the United States administration revoked the ban on commercial fishing within this monument. It is a decision that has caused profound concern among oceanographers and conservationists. Seabirds thrive only when there are sufficient forage fish, and opening these waters to commercial nets forces parent birds to expend far more energy to find meals for their young. Furthermore, the heavy gear used in bottom trawling can crush 1,000-year-old corals in an instant. It is a stark reminder that our oceans are not just economic resources, they are delicate, interwoven tapestries of life. Pull one thread and the whole system can begin to unravel. Of course, when we design these sanctuaries, we must remember to look deeply. In New Zealand, researchers have been studying the rocky reefs of the Poor Knights Islands. We tend to focus our conservation efforts on the shallow sunlit waters because they are accessible and easy to survey. But the researchers found that simply protecting the shallows is not enough. Just 50 metres down, in what we call the mesophotic zone, the marine community changes entirely. The deep water sponges found there are ecologically distinct. They are not merely deeper versions of the shallow reefs, they are unique specialists. Less than a third of the sponge species found in the shallows can survive in the deep, and vice versa. As our oceans warm and marine heat waves become more frequent, we cannot simply assume that the deep reefs will act as a universal backup or refuge for shallow water species. If we want to safeguard the true spectrum of marine biodiversity, our protected areas must encompass the entire profile of the reef, from the sunlit surface all the way down to the twilight limits of light penetration. And we must never forget that human communities are part of this ecosystem too. True conservation requires a profound respect for the people whose lives are tethered to the sea. In the Shetland Islands, local multi-generational scallop and creel fishers are currently voicing deep frustration over the expansion of industrial salmon farming into their traditional, highly productive fishing grounds. It is a quiet form of displacement, where the push for aquaculture inadvertently squeezes out small, sustainable local fisheries. Conversely, when communities are empowered, the results can be miraculous. In the Arnavan Islands of the Solomon Islands, local communities have successfully managed the South Pacific's largest rookery for the critically endangered hawksbill turtle. By combining local stewardship with global conservation standards, they have brought the turtle population back from the brink. Similarly, in the Yucatan Peninsula of Mexico, the coastal community of Rio Lagartos has just installed the first of hundreds of artificial reef structures. These underwater mountains will restore biomass, support local fishers, and create new opportunities for ecotourism. The ocean is resilient, but it requires us to be thoughtful, cooperative, and deeply informed. To be informed, we require data. We need eyes and ears out on the vast, unforgiving water, and that brings us from the macro world of global ocean governance to the micro world of our work here at Kalopa Robotics. The development of these robust, self-sustaining robotic sailors has been greatly accelerated by a wonderful, punishing event known as the Microtransat Challenge. The Microtransat Challenge is a transatlantic race for fully autonomous boats. It was conceived nearly 2 decades ago as a way to stimulate the development of marine robotics through friendly international competition. The premise is deceivingly simple. Build a boat no longer than 2.4 meters, launch it from the coast of Europe or North America, and have it navigate its way entirely autonomously across the Atlantic Ocean to a finish line on the other side. No human intervention is allowed once the boat is released. Over the years, the Microtransat has seen a rich and varied history of teams taking part. University students, retired naval architects, and cutting-edge robotics firms have all cast their small creations into the sea. And for many years, the ocean won every single time. Boats would be caught in fishing nets. They would be battered to pieces by winter gales. Some would suffer catastrophic electrical failures, their satellite trackers going dark, leaving them to drift silently as ghost ships in the vast Atlantic currents. Others would become hopelessly entangled in massive mats of sargassum weed, unable to steer or sail. But failure in science and engineering is just data by another name. Every lost boat taught the community something new. We learned how to build stronger rudder linkages. We learned how to write smarter algorithms that allow the boat's computer to read the wind direction and adjust the sail trim with the delicate precision of an experienced human sailor. We learned how to conserve battery power during long, overcast days in the doldrums. Finally, after years of collective heartbreak and innovation, the Atlantic was conquered. Small, uncrewed vessels proved that they could survive months at sea, navigating thousands of miles of open water, arriving battered and covered in gooseneck barnacles, but victorious. The legacy of the Microtransat Challenge lives on in the DNA of the Kalopa fleet. It proved that long-duration, autonomous ocean observation is not just a theory, it is a practical reality. Think back to the marine protected areas we discussed previously, the vast newly established sanctuaries in the high seas, or the deep water coral reefs off the coast of New Zealand. Monitoring these remote areas using traditional crewed research ships is prohibitively expensive and leaves massive gaps in our data. But imagine a fleet of small, silent, wind-powered robots patrolling the boundaries of a marine sanctuary for months at a time. They could use acoustic sensors to detect the engine noise of illegal fishing vessels, transmitting the coordinates via satellite to local authorities. They could monitor the temperature and salinity of the water, providing real-time data on marine heat waves. They could track the migration patterns of whales and sea turtles, ensuring that our dynamic protection zones actually follow the animals they are meant to save. This is the future we are working towards at Kalopa Robotics. A future where our technology works in quite harmony with nature, helping us to understand and ultimately protect the great blue heart of our planet. As our fleet rests and we prepare for our next deployment, we remain ever watchful and ever in awe of the ocean that sustains us all. Thank you for spending this time with me today. If you share our deep respect for the sea and a curiosity for the technology we use to explore it, please do subscribe to the podcast on your favourite platform. We will be back next week with more stories from the workshop and hopefully soon new telemetry from the open water. Until then, take care of yourselves and take care of our oceans. Goodbye for now.